In this video, we are going to work out the integral of 1 over square root of x squared plus 4. So in class, we already did this using trig sub. And the tip off to try trig sub is if I see something that looks like the square root of something squared plus something squared, or the square root of something squared minus something squared, I can often do trig sub. But now I want to work this out in another way. It turns out we can do this using our hyperbolic inverse function. So our hyperbolic inverses. And there's a key thing we have to remember, which is we've seen something very similar to this function before. If I flip it back a couple pages, I've seen this thing with a plus 1 in the bottom. That's actually the derivative of hyperbolic sine's inverse. So another way to write that is, if I were to do the integral of this 1 over square root of x squared plus 1, then I get hyperbolic sine inverse plus c. So to be able to use this, I really need to have a 1 there, not a 4. So to get a 1 there, I'm going to factor a 4 out. So I'll start by factoring a 4 out. I'll get 1 all over, I got my big old square root, and then I'm factoring a 4 out, and that'll leave me with x squared over 4 plus 1, and then dx. So now this 4 that I factored out, I can square root it, which becomes a 2, and I can pull that 2 out in front. So doing that, I'll get a 1/2 in front, and then my integral of 1 over, and then I get big old square root. I got my plus 1. And now I'm going to rewrite this x squared over 4 to make it look more like just something squared. I'm going to put a big old parentheses squared. And then what has to go inside it is a x over 2. Because if I do x over 2 and I square it, I'll get x squared divided by 4. Okay, and of course I got the dx at the end. So now this is looking more like what I have here, except, well, I have this x over 2 getting squared rather than just x getting squared. So to make it look more like that, I'm going to do a u sub. Let's let u be x over 2. And then the derivative, du, I'll just get 1/2. And then, of course, I got to put the dx next to it. So I'm doing this u sub. And I noticed that, okay, there's this 1/2. I could put that back in, and then 1/2 with the dx, that just becomes du. Okay, so that's pretty nice. So I get my integral of 1 over, I know the 1/2 and the dx, that just becomes that du. And on the denominator, I get the square root of, and now I'm subbing in, I'll get u squared plus 1. And now that finally looks like the integral that I know. This is going to be my inverse hyperbolic sine. So this is going to be my inverse hyperbolic sine of u, though, and then plus c. I got to plug back in for what u equals. So that's going to give me inverse hyperbolic sine of x over 2 plus c. And that is my antiderivative. But if I compare it to what we got using trig sub, it looks pretty different. Like this has an ln. It turns out they're actually the same if I use this identity for what hyperbolic sine is in terms of logarithms. So I'm going to recall we had shown this formula that our hyperbolic sine inverse equals ln of x plus the square root of x squared plus 1. So we had shown this at some point during class. I'm going to use this. And essentially now I'm going to just, instead of, don't mean to erase, wherever this x is, I'm going to replace it with an x plus 2. So I'm going to be plugging that in here for this x and for that x. So doing that, I get ln of, and I'll get an x plus 2 plugged in, and then plus big old square root, and then I'll get x squared over 4 when I square the x over 2, and then plus 1, and then plus c. And now it's looking quite similar. Like I have this x over 2 like I need. It turns out this square root, if I get a common denominator and I simplify it just a smidge, it'll turn into this thing. So that's good. The only other difference is that this natural log has an absolute value and this one doesn't. And it turns out that when we did it in class, I actually could have removed this absolute value. And the reason for that is, well, this whole fraction here is going to be positive because I have this square root, and no matter what gets plugged into the square root, the output needs to be non-negative. So this whole thing is going to be something that's positive. In fact, having the plus 4 here guarantees that it couldn't even be 0. It's got to strictly be positive. But then, well, the square root of x squared plus 4, that's bigger than just the square root of x squared, right? If I make the inside smaller by getting rid of the 4. But that right there, this square root of x squared, that actually equals absolute value of x. And absolute value of x, well, that's greater than or equal to this numerator, x. So overall, it means that this first numerator is bigger than this second numerator. And that's going to make this first fraction bigger than this second fraction. Okay, this one potentially could be negative, but overall, this one's going to be positive and bigger overall, kind of net, when I look at its absolute value. So because of that, it's going to make this whole inside thing be positive. And the absolute value of a positive thing is just that thing, so that'll allow me to just write parentheses rather than absolute values. So that does confirm that both of these actually are the same. Okay, and there we have it. So for problems like this, like these formulas for the derivatives of these inverse hyperbolic sines or trig functions, I wouldn't expect you to have these memorized. These are things that, like on a quiz or on a test, I would provide you with these formulas.